Hello children. In the last video we have discussed what is light, what is reflection, what are the types of reflection, what are the laws of reflection and image formation due to a plane mirror and lateral inversion. So I'll leave the same video in the cards. You can go check there. That is the first part of the video. In the second part, in this video, we are going to discuss about spherical mirrors. Spherical mirrors. The name itself says spherical in the sense sphere. So generally if we consider a sphere, it can be a hollow sphere or it can be a solid sphere. If there is no space at the center or inside the sphere, that is said to be as a solid sphere. Whereas if there is a space inside the sphere, that is said to be as a hollow sphere. Now here we will study the mirrors which are taken from a sphere, such that they are called as spherical mirrors. And what is a sphere? In simple words, we can say a ball is in the shape of a sphere, right? So that ball, if we consider a tennis ball, okay? So that is which is in the form of a sphere. That is for an example. Now if we consider a reflecting sphere, what is this reflecting sphere? Okay, so it must be reflecting some light. This is what you came to understand, right? So yeah, if we consider a sphere, why did I draw a circle then? If this is a sphere, the 2D form of a sphere is circle. Okay, if this sphere is coated outwards, such that the inside portion of the sphere is a reflecting surface, whereas the outside portion of the sphere is a coated surface. And we know, where should we incident the light rays? Obviously on the reflecting surface. So this is one kind of sphere. Let us consider another kind where the coating is done inside. Now the outer portion of the sphere is a reflecting surface. Fine now? Yeah. So we have taken one sphere where the outer portion is actually painted with silver and the inner portion is the reflecting surface. And here what did happen? We have took the coating inside, silver coating inside the sphere, and outside it is a reflecting surface. Now let us consider a smaller part of this sphere. Let me draw this sphere larger so that you can understand easily. Okay, so in this way, let us consider the sphere is coated. This sphere is coated. Now let us consider a part from here to here. That means this reflecting sphere is made into two pieces. This is one piece and this is another piece. And now if I draw that piece aside, now what did we come to know here? This is a reflecting surface. Whereas this is a coated surface. Now if you see this reflecting surface is caved inside. It is drooped inside or caved inside. Such a type of reflecting surface or a reflecting mirror or a spherical mirror is said to be as a concave mirror. This is a concave mirror. And obviously you know what is this type of mirror. Let us see. Even let us take a small part from here, such that becomes in this way. If you carefully observe, the inner part of the sphere is being coated here. right? And the outer part is the reflecting surface. So this is the reflecting surface, whereas this is, what is this? This is coated surface. Now if you see, this reflecting surface is actually vexed outside, or it is bulged outside. Vexed outside, bulged outside. So such type of spherical mirror is said to be as a convex mirror. Convex mirror. So clear now about the two types of spherical mirrors. Why are they called as spherical mirrors? Because they are taken from a reflecting sphere. And what are the two kinds of spherical mirrors? Concave mirror and convex mirror. Now in order to learn this deeply, we require some of the terms. What are those terms? Let us see. Obviously, no. See, whenever you want to study how actually the pen works, just how it writes, okay, you'll obviously test a pen. And you'll have a reference with a pencil, or can be with a lightener or something like so. Highlighter, it can be said as, no problem. So now let us consider these spheres. Let us consider this sphere, okay, which is actually coated outside, no problem. Let us consider this is coated outside, but still this is a sphere. It will have a center. Obviously, we know the sphere as well as circle will have centers, and those centers will not be shifted. The sphere is made into a 2D. It is called as a circle, but still it is having the same center. So the center of the sphere from which the spherical mirror is taken, I repeat, the center of the sphere from which the spherical mirror is taken is said to be as center of curvature. Center of curvature is said to be as a center of curvature. Now, obviously, this circle or the sphere will have radius r, and this radius is equal. Why this radius is equal? Whenever we study about a circle, what is the definition of a circle? A group of points equidistant from a single point. A group of points equidistant from a single point is said to be as circle. And what is radius? The distance between any point on the circle to the center of the circle is said to be as radius. So obviously we do have n number of radius for every point which is on the circle is having a radius which connects it to the center. Right. So obviously radius of curvature is the second one. Which you are going to study, second term which you are going to study, and it can be defined as, radius of curvature can be defined as the radius of the spherical, the radius of the sphere from which the spherical mirror is taken. Okay. Radius of curvature. Radius of curvature. Center of curvature is denoted by C. Radius of curvature is denoted by capital R, capital C and capital R. Clear with this, no? Now, we obviously know we're going to study about spherical mirrors, not the complete sphere which is actually reflecting the light. Clear, no? So now, if we take this part aside, this will obviously become a concave mirror because the reflecting surface is caved inside. Clear, no? Yeah. So there is a center over here, and this is the radius of curvature, and this C is said to be as center of curvature. Now we should have another reference here which is said to be as pole. pole of the spherical mirror. What is this pole, sir? Pole of the spherical mirror, capital P. The pole of the spherical mirror is the geometric center. Geometric center of this spherical mirror. So what is this center of geometry or geometric center? Now align a thread in such a way it actually stays on the boundary of this spherical mirror. In simple words, let the thread be on this spherical mirror. Obviously, you'll get some length, no? Maybe if I guess, if it is about some 20 centimeters. Okay. Now the center of that is said to be as a pole of that mirror. Pole of that mirror. Let us consider this is the geometric center of the length of this concave mirror, which is termed as pole of the spherical mirror. I have taken a concave mirror, you can take convex also, no problem. But if you consider convex, let us see what will happen. Consider this is a convex mirror which is coated inward, see. And how is the curve actually? It is vexed towards me. So obviously center of curvature will be here because group of points equidistant from a single point. And radius of curvature R and pole P. But if you carefully observe what has happened here, here center of curvature and radius of curvature, okay, are towards the reflecting surface, whereas for a convex mirror the center of curvature and radius of curvature are towards the polished surface. How clear is this? Clear with this now? Yeah. And we do have another term called aperture. See, this aperture is randomly asked in your board exams or even in your other types of exams, formative, summatives, assignment tests, some other pre-finals, this kind of. So what is this aperture? It is the diameter of, say for example, see, though we have taken the 2D of this concave mirror, but still this is not the concave mirror. This complete thing is said to be as a concave mirror, right? So now the distance, so obviously what will happen? This seems to be a circle in this way. If the face is towards the camera or towards you, this seems to be a circle. Obviously for that concave mirror or even for the convex mirror. So this circle will obviously have radii, which are said to be as radius of curvature, and they will be obviously having diameter also, because every circle has a diameter. Now the length of that diameter, is said to be as aperture. And you may ask me, so sir, if the length of that diameter is aperture, then it must be double of the radius of curvature, no? No. Because radius of curvature is the radius of the reflecting sphere, not that circle. But this circle's diameter is aperture. Clear with this now? Yeah. And in order to study the next term which is actually involved, we will study how the light rays will actually behave when they are incident from infinity onto this concave mirror, even onto the convex mirror. Let us see. Let us consider a concave mirror. Concave mirror, you can even consider a convex mirror, but that will become a virtual incidence. That we'll see. Okay, sorry, virtual reflection. Now, this is the pole. This is the center of curvature, and this is the radii. Okay. Now, before going to know what is focus, first we'll study an imaginary line which connects this center of curvature to the pole, and this imaginary line is again for reference, and it is termed as Principal axis. Principal axis. Principal. It's not your principal or my principal. Obviously, principal is a administrator. Obviously, here also this guy principal axis is a administrator. He is a bigger reference. That is why he must be considered, and he is principal axis. Principal axis is the imaginary line which connects the center of curvature to the pole of the spherical mirror. To the pole of the spherical mirror. Fine. Now let us consider an object. So generally, what is the object we take? It is just an arrow, a rect arrow, and it is placed somewhere in the infinity. Let us consider it is not on the principal axis. It is placed somewhere in the infinity. Okay. So now let us consider. There is an incident ray from infinity onto the spherical mirror. Okay. Now that ray must be whatever the ray we are taking, that must be parallel to this principal axis. Why should we take that parallel rays? That also we'll study now only, just in a minute. Now this ray will actually reflect from this concave mirror and meets the principal axis at a point called focus. Meets the principal axis. Which ray? The reflected ray. At a point called focus. So in this way, if you even take another ray which is actually parallel to principal axis, they reflects back and passes through focus. Again, this is also a reference, this focus. Okay. Now coming back to our doubt. Sir, you were discussing about something called a parallel ray. Why we should incident only parallel to the principal axis? Okay. So it's so simple, Nana. It's so simple. Here we are going to study the light rays with the reference. So they must be parallel to principal axis. And those light rays which are parallel to principal axis, these parallel rays to principal axis are said to be as parallel and parallel to principal axis. Parallel and parallel to principal axis. Para-axial, which are also in simple words paraxial rays. Clear now? Why should we use only paraxial rays? Because when the principal axis is taken as a reference, the only rays which are parallel to that can be studied clearly. And there are some other type of rays which are said to be as marginal rays. Marginal rays move in random. They are parallel, they are not parallel. So this type of rays are said to be as marginal rays. And marginal rays, obviously we will not use them to study the behavior of reflected ray when an incident ray is incident onto the spherical mirror. Clear with this now? Everyone? Fine. So now this point is said to be as focus. What is that point? Whenever light rays are incident from infinity onto a spherical mirror, they reflect back and pass through focus. And the distance between the pole and focus is small f, which is said to be as focal length. What have we studied? Focus we have studied, which is capital F. And what is focal length? The distance between the focus and pole is said to be as focal length, and it is actually denoted by small f. Clear with this now? So what have we studied? We have studied what is principal axis, center of curvature, radius of curvature, pole, aperture, focus, focal length. These are all the references. So by using this, now we will study object distance, image distance, object distance and image distance. Okay. Okay, by on the diagram, obviously I'll show the same to you in the very near, maybe within few minutes. But for now, the definition can be given as the distance between the pole and the object. This distance is u, and this u stands for, what is this u? Object distance, small u nano. Okay, so the distance between the pole and the object is said to be as object distance. Every time if you want to specify capital R, you can specify, otherwise no, it is not actually required. Small f is also not actually required, but their lengths are equal and there is a relation between radius of curvature as well as focal length, which we'll discuss now. Now, say for example, if the image is formed, actually this is one case of image formation due to a concave mirror, and where will be the image formed for this? In the sense, it is formed between center of curvature and focus. That we will see in the near future. Okay, now this image, the distance of this image from the pole is said to be as image distance. Image distance is said to be as image distance. Clear with this now? The distance between the pole and the image being formed is said to be as image distance. Sir, how are these images are actually formed? That we will see. The image formation due to the spherical mirrors, convex mirror as well as concave mirror. That will be discussed, because first we have to study how actually these reflections takes place. See, if it is a plane mirror, you might have taken angle I is equal to angle R, sir. Obviously, I'll come to know for which amount of incidence, how much reflection it must take place. This angle you will consider, you will say angle I, sir, which is equal to angle R, sir. That's why I have taken it in this way, sir. But when it is curved, it is not like how the normal will be confusing here. How is the normal? Obviously, no. Because this is a plane one, and what about the normal here? How can you consider the normals? That let us see now. Okay. Now let us consider a circle with a center C. Let us consider a circle with a center C. Consider this as a circle. This may seem like your masala dosa, but no problem. Consider this like a circle C. Okay, and we know there will be very bigger number of radii. See, we know circle is, there will be many points here. These points are equidistant from one point, which is center. The collection of those points is said to be a circle. So every point will have radii, but I have taken only some of the radii. Okay, all these we know, all these radii are equal. Okay, so this is radius even, this is radius, this is radius, this is radius. Let us consider point A, point B, point C, point D on the surface of the circle. Now, at every point, let us consider a tangent. Oh, why? Sir has come up to tangent also, because he is going to consider what is normal here. If we want to study what is normal, we have to study about tangent. Okay, so now if you consider what is the angle between the radii and tangent of a circle? 90 degrees, sir, we know. It's 90. It's a right angle between radii and tangent. Radii and tangent. Clear with this, no? Yeah. So now if you carefully observe, let me take this part. How is this part? See, there is one radii here, another radii here, another radii here, another radii here, and there are some tangents here. Okay. How are these radii? They are in 90 degrees with these tangents. They are in 90 degrees with these tangents. That means on the surface, if we are going to say, for example, this point A, at this point A, if we are going to incident, let us consider this is a concave mirror. So if you are going to incident light, incident ray, this angle I must be equal to another ray. I mean angle between another ray and a normal, which is angular. So by this we can conclude that the radii itself behave as normals. The radii itself behave as normals to the reflecting surfaces, which are actually taken from a sphere and said to be as spherical mirrors. Okay, so what are the normals? Radii itself are the normals. Clear now? And now let us consider clearly once more. Okay, now there is a concave mirror as well as a convex mirror. Center, and this is one radius. Consider a light ray coming in this way, parallel to principal axis. We know, because paraxial rays will give us more amount of study. So now at this point, this will become the radii, because for this point, the line which actually connects the center of curvature to a point is said to be as radii R. Now this reflects in such a way the angle between the radii and incident ray, this angle is equal to this angle, and this is RR, reflected ray. So now if you see whenever the light ray is incident parallel to principal axis, it reflects back, and it is found, it is not discovered, it is not assumed, it is found passing through focus. It is found passing through focus. Let me take another ray, even from here. Then obviously when it is parallel, it will be found. See, this will be the normal. Sorry. This will be the normal, and it will be reflected in this way. This is RR1, this is IR1. It is found to be passing through focus. And how are these light rays reflected light rays? They are moving towards each other. That means this beam is moving towards each other. What is the beam which moves towards each other? It's a convergent beam. It's a convergent beam, and hence this spherical mirror, which actually has reflected rays as convergent beam, is termed as converging mirror. Converging mirror. Converging mirror. See how simple is this? You have to understand that radii are the normal. And what happens here? Now, this is untypical. This is so very typical because the center was actually inside the reflecting surface, but this one is untypical. It is different. Okay. Now, if you consider this can become the center of curvature, and let us consider this is the radii. If that is the radii, I have to extend this. Okay. Now, this is the pole. Now light is incident parallel to principal axis. Incident parallel to principal axis. Now what happens actually? This is a bigger confusion. Radii, this can be termed as radii or radius. Radius. This is the normal actually, but what is happening? Incident ray is coming, but it has to bounce back into the same medium because it is a reflection. That is what is the definition of reflection, no? So now this should be extended in such a way, this will be taken as the normal at this point of incidence. So obviously to satisfy angle I is equal to angular, not to satisfy, but actually practically it is seen angle I is equal to angular. That is why it is made into a law. Okay. So this angle will be equal to this angle, angle I, angle R. But here if you see, if I take another ray, incident parallel, obviously this is the normal. When this is the normal, angle I is equal to angle R, no? Because if I extend this normal, this angle, angle I1, angle R1. But these rays are moving away from each other. If you consider R and R1, they are moving away from each other. And what is this kind of beam called as? It is said to be as a divergent beam. Divergent beam. And the type of mirror is diverging mirror. Zing. Amazing if you have seen the film. So divergent beam and diverging mirror. How simple is this? That is why if you study about the normal, see, generally if you open your book and try to read, you may understand many things. But what about the normal? There is a confusion for you. Sir, you said reflection is valid. Either it can be a regular reflection, irregular reflection, clear mirror when the light is reflecting from a stone or a body or an object, whatever. Wherever there is reflection, there the laws of reflection are valid. So obviously they must be valid in spherical mirrors also. Yes, they are valid. But in order to take angle I is equal to angular, where is the reference normal, sir? That is what I have said to you, sir. The radii itself are the normal. So if you consider that, in this way you can easily understand how to take the reflection, I mean reflected ray for a converging mirror as well as the diverging mirror. Okay, I repeat again, which is the converging mirror? Concave mirror is the converging mirror. Which is the diverging mirror? Convex mirror is the diverging mirror. Diverging mirror. Okay, so before going to image formation, let us study some of the standard measurements and relations between these terms. Standard measurements. So if we consider the standard measurement of the image compared to measurement of the object. Okay, so let us consider the height of the image. The height of the image. Height of the image. Height of the image. Okay, when it is compared to height of the object. Sir, why should we compare, sir? If you compare only, you will come to know which amount of change the image has taken when it is compared to the object. Say for example, if I stand before a plane mirror, the size of the image which is formed on the mirror is same as the size of mine. But if you consider spherical mirrors, they will have different sizes of the images when they are compared to the sizes of the objects. So obviously we should have a measurement which actually is the ratio of height of the image to the height of the object, and that is termed as magnification, denoted by small m, is equal to height of the image, which we generally take it as hi, and height of the object is taken as h suffix o. These are suffixes. Do not put I in adjacent to h. It must be kept as a suffix. Clear now? So magnification m is equal to height of the image to the height of the object. Why is this important? Why is this important? Because of the applications, and that we will see in the future. Okay, applications we will obviously discuss when we discuss the image formations due to the spherical mirrors, which are concave and convex mirrors. So this is one of the term which is actually used to measure the properties of image to the properties of the object. The radius of curvature is related to focal length as r is equal to 2f. The radius of curvature is twice the length of the focal length. The radius of curvature is twice the length of the focal length. So r can be given as radius of curvature is twice the focal length of a spherical mirror. Okay, so magnification is one property which is actually comparing the image to the object, and the focal length is related to radius of curvature as f is equal to r by 2. F is equal to implies f is equal to r by 2. This is about the relations. Okay, so before going to form the images due to the spherical mirrors, that means image formation due to the spherical mirrors, we have to study first how should the light ray behave, that means how should the reflected ray behave for the incident ray. For that we have some set of rules called ray rules of spherical mirrors. They may ask you, what are the set of rules which must be followed in order to draw the image formations due to a spherical mirror? Okay, those set of rules, they are of three types. The first one, whenever the incident ray is parallel to principal axis, say let us consider a concave mirror. Okay, and we'll consider one convex mirror also. What's wrong in taking this? So pole, focus, center of curvature. Even for this, pole, focus, center of curvature. Now the first ray rule says whenever the incident ray is parallel to principal axis, it reflects back and passes through focus. This is a standard ray rule which is observed and made into a rule. So I repeat, when the incident ray parallel to principal axis reflects and passes through focus. So here you may assume a normal. See, once you are drawing the image formations, okay, can be in your notes, can be in exam or anywhere, no need to draw the normals here. But keep in mind, angular is equal to angular, and incident ray, reflected ray and normal lie on same plane is valid. Okay, and if you have that doubt, this is a point, and obviously if we consider a plane here, plane at this point, so their xy dimensions are quite enough in order to study all these three rays. That's why they are said to be S2D, and they all lie on the same plane. Clear, no? Now let us consider incident ray parallel to principal axis. Sir, but how can the light ray go into the is this reflecting surface? Coated surface, sir. How can this light ray go into the coated surface, sir? Which is not actually possible, no. This seems to be passing through focus. Seems to be. It's a virtual reflection. See, whenever the light ray is directly reflected back without the presence of virtual reflection, this type of reflection is a general real reflection, and those images which are formed by those real reflected rays are real images. And here there is a virtual, because this seems to be meeting when it is extended in the opposite direction. Seems to be meeting. Seems to virtual. Originally real. Seems to virtual. Originally real. Clear, no? Yeah. So this seems to be intersecting the principal axis at a point called focus. So even for a convex mirror, whenever the light ray is incident parallel to principal axis, the reflected ray passes through focus virtually, really. Clear with this, no? Right. The second ray rule. The second ray rule is inverse of this. What is that inverse? Simple. Let us see. Now the light ray is actually incident through focus. Incident through focus. So if I consider a light ray incident through focus, this reflects back parallel to principal axis. That's it. That reflects back parallel to principal axis. Inverse of it. Here also, it is incident through focus. Again, you may ask me the doubt, sir, should I incident through focus, which is actually inside the coated surface, sir? No, sir. That is not required. Virtual incidence is considered. Virtual incidence. And now the reflected ray is parallel to principal axis. Parallel. Clear, no? Yeah. We have studied two ray rules. There is one more simple single ray rule. Simple single ray rule, which is actually angle I is equal to angle R only. Obviously, no? That is obviously obvious everywhere. Okay. Now let us see that. But here what we will see is, we will incident it on the pole. We will incident it on the pole. And let us see how this actually behaves. Angle I is equal to angle R only, no, sir? We can simply draw, but there is a point of consideration here. Okay, the third ray rule, I'll take a concave mirror, and a convex mirror. I'll take a concave mirror and convex mirror. Pole, focus, center of curvature. Pole, focus, center of curvature. Now, whenever the light ray is incident onto the pole, again if you consider, even at the pole, what is that? There is a point. Again, definition of circle. Set of points. So even the pole is a point. Okay. And the distance between this center of curvature and the pole is again R only. So obviously when this is considered as a radius, this is the normal, and this angle I is equal to this angle R. That is what. It's so simple. The third ray rule says, whenever the light ray is incident onto the spherical mirror, and if the radii is considered, is the normal, the angle of incidence is equal to angle of reflection. Okay, the same happens here. This is the virtual normal. Angle I, angle R. Done. Okay, let me repeat the three ray rules. What is the first ray rule? For a spherical mirror, whenever the incident ray is parallel to principal axis, it reflects back and passes through focus. Second ray rule, whenever the incident ray is incident through focus, it reflects back parallel to principal axis. Third ray rule, wherever the incidence is on the spherical mirror, it follows angle I is equal to angle R. And now, by using these simple ray rules, in the next part, we are going to discuss about the image formations due to the spherical mirrors, which are concave mirror and convex mirror. And if you are up to here, try to support me by subscribing. And if this lecture is interesting, please share the same to your classmates such that they will also gain some knowledge even some knowledge from my videos. Thanks for watching. This is Naresh Ramraj. Bye bye for now. Have a good day.